Hello, this is Prateek Karkera and I'll be presenting our research on optimization techniques of quantum neural network for image classification alongside Dr. Srivaramangai from the Department of Information Technology, University of Mumbai. Firstly, we'll go through the outline for the presentation in which we'll touch on the introduction to the quantum techniques followed by the problem statement being addressed and the methodology used in this research and then the results and observations from the experiments followed by the conclusions drawn from this research. Now with the outline hyperlink below, we'll first move on to the introduction. Introduction, as we all know, quantum computing is an emerging technology which uses the principles of quantum mechanics, offering the potential for exponentially higher, accurate, and efficient image classification results. Now, qubits, which are basically the quantum analogs of classical bits, can exist in multiple states simultaneously, and this phenomenon is known as superposition. Qubits also showcase another peculiar property called quantum entanglement, which is a unique property where qubits become correlated and the state of one qubit is directly related to the state of another, even if they're physically separated. This property can be harnessed in image classification to capture complex relationships and dependencies among pixels or features. Moving on to the problem statement being addressed. Now, quantum computing is still in its early stages. Dealing with resource constraints such as limited qubits will lead to inaccurate results and very slow performance at times. Previous studies have showcased the potential for quantum-based methods, but quantum algorithms can be computationally expensive, especially for complex datasets and complex imagery. This gives the need for optimization techniques, which are very crucial for efficiency, improved accuracy, and practical application of quantum techniques in the real-world usage of quantum techniques. Now, this research aims to experimentally compare various optimization techniques with the goal of making quantum models more efficient for practical use in image classification tasks. Moving on to the methodology, which consists of four sections: data acquisition and data pre-processing, PQC, which is parameterized quantum circuit and the image encoding, training of the quantum neural network and optimization, and the performance evaluation and the results. Now, moving on to the data acquisition and pre-processing part. This study uses nebular images of size 4096 by 4096 pixels from the NASA Image and Video Library. These images serve as a representative dataset for diverse applications such as medical imaging exercises, which are particularly relevant for domains which require intricate patterns and feature extractions. Now, in this study, two sample sets are used for classification and optimization, consisting of 50 and 100 images each, respectively. Images are resized and partitioned to capture intricate details. They undergo binarization to enhance the contrast, and they are represented as flattened, normalized vectors to prepare them for the classification. The 6-qubit circuit 15 proposed by Sim et al. Is used as an exemplary quantum circuit design for the quantum neural network used in the study. The quantum circuit design is designed using the Qiskit library, and for the encoding and parameterized quantum circuit part, the encoding circuit creates a superposition of quantum states representing the input data. Hadamard gates are applied to each qubit to initialize a superposition state. Now, in case of encoding, the circuit then applies a RY rotation gate. RY rotation gate is basically rotation along the y-axis to each qubit, where the pixel value of each image is encoded into the quantum circuit by adjusting the theta rotations on the individual qubits. In case of PQC, the theta values of the PQC or the parameterized quantum circuit, the theta value of the RY gates are adjustable depending on the parameters used for our optimization. These are the parameters that we're looking to optimize. The application of controlled X or the CX gates, control not gates, creates entanglement between the qubits, which introduces correlation between the qubits. The circuit is encoded by the image pixel values and then further modified by the PQC, which introduces additional RY rotations and CX gates, in which the value depends on the parameters of the quantum circuit. Next comes the classification, the training of the quantum network, and the optimization techniques used. The output of the classification is obtained by the final measurement of the state after combining the encoding circuit PQC and then quantum neural network. The PQC captures essential information from encoded data, connects the quantum circuit to the optimization models for training and classification. The quantum neural network training then involves adjusting the PQC weights with various optimization techniques, including gradient-based optimization techniques, then Adam-based optimization techniques, as well as quasi-Newtonian methods such as LBFGS, which are processed by the entropy loss function. A defined closure function is then iteratively updates the model parameter during the training, and accuracy is evaluated by comparing the predictor class labels or test data. Moving forward, the performance of the model is evaluated using the accuracy, precision, recall, and the F1 score values. Now, each model's competence is correctly classifying instances across the two different classes evaluated using the confusion matrix, precision recall, and the F1 score. From the two datasets used in the study, the results of the first dataset comprising of 50 images gave the following results. The initial accuracy rate of the base QNN model was 0.46 or 46%. The optimization techniques significantly enhanced the model's performance. The LBFGS algorithm achieved the highest accuracy rate of 0.92 or 92%, demonstrating exceptional effectiveness in optimizing parameters. RMS prop algorithm displayed notable accuracy with a rate of 0.88, exhibiting balanced efficiency score. Adam-based methods, however, showed lack of effectiveness in enhancing the model's performance for the given data. Now, for the second larger dataset consisting of 100 images compared to the previous 50, for the second larger dataset, the goal here was to understand the impact of a larger dataset on the performance metrics. Now, again, LBFGS displayed higher precision recall and F1 scores for both classes across all models, achieving an efficiency rate of 95% in correctly classifying instances from both classes. LBFGs and RMS prop demonstrated success again, indicating specific optimization characteristics suitable for QNN models in this context. This can be attributed to the nonlinear nature of the quantum models. R-Adam, SGD, and ASG models show significant efficiency improvements corresponding to the increased quantity of images. Now moving on to the conclusions drawn from the research. Significant improvements were made during the optimization process to enhance the QNN or the base quantum neural network model. LBFGS and RMS prop optimization outperformed other techniques, with LBFGS achieving an impressive 95% accuracy. Now, greater potential for optimization effectiveness can be demonstrated when a larger number of images is considered, as we saw in the second result. Now, this research successfully underscores the importance of exploring various optimization techniques in the quantum machine learning base. In the optimized quantum models provide practical insights into quantum computing's usability for practical use cases of classification tasks. Now, while showcasing potential, future efforts should prioritize algorithmic development, scalability, and addressing limitations in the quantum hardware, such as the restriction on the number of qubits used, and the stability and the noise correction. So that's it from the research, and thank you so much for giving the opportunity to present our research. Now, signing out. Thanks.